Okay, in this video we're going to pick up where we left off from our discussion prior. We've already looked at L'Hopital's rule, and now we're going to spend a little bit of time talking about what we call improper integrals. Now, an improper integral is an integral that is trying to be computed on a graph that never quite reaches zero, for example. There's kind of an infinite distance along this x-axis, but no matter how far we go, we have some minute height here. And we'd like to be able to calculate a specific or discrete, well, discrete's the right word, but we'd like to compute a finite value, let's call it that, for the area underneath this curve. Now, we know theoretically this value never quite reaches zero, so it's technically an open shape that doesn't bound an area. But as it turns out, we would say whether or not the integrals converge or diverge. Now, if the limit that we compute in the examples that I show, if the limit does exist, or if it is something that we can compute, then we would say that the integral converges, and we will decide on a specific area for that integral. If the limit doesn't exist, then we would say the integral diverges, and therefore we can't calculate the area underneath the curve. So let me show you what I mean as an example here, and then we'll talk about these conditions that are shown in the chart on the left. In question A, we've got the graph e to the negative 3x. Now, e to the 3x would be an exponential function that grows from left to right. E to the negative 3x is one that decays from left to right. So it's going to look something like this. Now, the graph itself never does quite reach zero. It gets relatively close, and infinitely close for that matter. And we're trying to calculate the area between 0 and infinity on the x-axis. So we're trying to figure out what this area would be over here to the right. And that seems a little bit difficult to do at first, but with our technique for improper integrals, we can make this happen. Now, what the instructions over here were telling us is that if we have a boundary on the right-hand side of our integral, then what we will do is we'll replace that integral with some value b, and then since b is supposed to represent the number infinity, we'll just calculate the limit as b approaches infinity of this integral. Now, doing so is going to require us to do some of this integration by hand, so let's get some practice here. Question A. The result for question A is going to be the result of the limit as b approaches infinity of the integral from 0 to b, e to the negative 3x dx. Okay, well, this limit then would be equal to the limit as b approaches infinity of the result of this integral. Now, this integral is going to require the antiderivative of e to the negative 3x. Well, that's e to the negative 3x times, I don't want to use the grouping symbols though, times negative 1/3. Okay, so this k value against our variable up here is going to come down out front when we find the antiderivative. And we need to evaluate this antiderivative between 0 and b. Now, according to our fundamental theorem of calculus, we will evaluate this antiderivative at two locations, once at b, so negative 1/3 e to the negative 3b power, and once again evaluated at 0, subtracting the 2. Negative 1/3 e to the negative 3 times 0 power. And again, we're trying to evaluate the limit of this expression as b goes to infinity. Now, this is effectively a direct substitution with the number 0 at this position, so we can just evaluate it. Negative 1/3 times e to the 0 power. Well, e to the 0 is 1, so we've got minus a negative 1/3, so we'll call that 1/3. And when we think about this component as b approaches infinity, well, as b approaches infinity, then this power becomes negative infinity, and e to a negative infinity goes towards 0. So that expression goes towards 0. 1/3 times 0 is also 0. I would say that the limit of this expression ends up being 0. So now we see the limit of this expression is 0 plus 1/3, or just 1/3. The area underneath this particular curve between 0 and infinity is 1/3. Let's take a look at another. Now in part B, we have the graph of 1 over 1 plus x squared. That's a graph that looks something like this. It looks remarkably similar to this example over here, although the peak of the curve is located at the origin for question B. Now in this case, we are again looking for an integral between 0 and infinity, so I'm going to follow this first pattern again. Even though the picture looks like pattern number 3, we're using this pattern number 1. We're starting at some arbitrary value and approaching infinity. Oh, you know what? I just recognized I used a different letter than before. No. Okay. All right, they did recommend using B here. All right. So here we go. In this particular case, we will say that this integral is equal to the limit as b approaches infinity. So our b upper boundary is infinity here, of the integral from 0 to b, now b is a number, of 1 over 1 plus x squared dx. Okay, so again, this limit's result is equal to this limit here, as long as we can find the antiderivative of 1 over 1 plus x squared. Now this looks like it may be a bit intimidating at first, but hopefully you recognize that this is a pattern that we've learned about in Calc 1. And the function whose derivative is 1 over 1 plus x squared is tangent inverse of x. So, since the antiderivative is tangent inverse of x, we will evaluate that at both 0 and b. And the limit as b approaches infinity of this is going to be tangent inverse of b minus tangent inverse of 0. Now, as b approaches infinity, we're basically asking ourselves on the domain of tangent, what angle measure is going to produce a result of infinity. Now, thinking back to our graph of tangent within its appropriate domain, we're talking about this graph here with a lower boundary of negative pi over 2 and an upper boundary of positive pi over 2. Now, theoretically, we can't evaluate tangent at pi over 2 because this behaves like a vertical asymptote. But if we're asking when does the function itself equal infinity, when does it approach infinity, well, the function approaches infinity as as this tangent inverse approaches pi over 2. So I'm going to say that this is pi over 2. Similarly, what angle is going to produce a result on the tangent function equal to 0? Well, the tangent function equals 0 when our theta, or when our angle value, is 0. So I'm going to say that as b approaches infinity, tangent inverse of b is pi over 2, and as b approaches infinity, tangent inverse of 0 is 0. b is not really in effect here. And so I would argue that the result, or the area underneath this curve between 0 and infinity, is going to be pi over 2. Actually, I'll just slide this drawing over instead of deleting it. Okay, so pi over 2 for part B. For the next group of problems, 5, 7, and 11, they behave just like the last two examples, so I would suggest that you try these on your own. And when you try these on your own, number 5 ends up coming out equal to 1, 7 comes out equaling 1 divided by e, and 11 ends up coming out equal to 1/2. But when we consider question number 9, we see an interesting result. So I'm going to jump over here and complete this one with you here. So we can approach this the same way that we've started the others. We can say that this result for number 9 is going to be equal to the limit as b approaches infinity of the integral from 2 to b. And I'm going to write this as 1 over square root of x dx. And better still, I'm actually going to write this not as 1 over square root of x, but to help me see the math a little bit more clearly, I'm going to call this x to the negative 1/2 power dx. Now, the limit then as b approaches infinity is dependent upon the antiderivative of x to the 1/2 power. So we can use our power rule for antiderivatives here. We're going to generate x to the positive 1/2 power because we have to increase by a power of 1 and divide that by 1/2. Now, dividing by a half is kind of tricky, so I'm going to change this to a multiplication of 2. So our antiderivative is 2x to the 1/2 power, and better still, we can call that 2 times the square root of x. There's our antiderivative, 2 times the square root of x. This antiderivative has to be evaluated at 2 and b. And as we do so, we see something that's kind of interesting here. 2 times the square root of b must subtract 2 times the square root of 2. Now, I'm not too worried about 2 times the square root of 2. That's just a number, but 2 times the square root of b, well, the limit of this expression as b goes towards infinity, as b increases towards infinity, the square root of infinity also increases towards infinity. And this thing is going to race off towards infinity. So since this limit approaches infinity minus 2 square root of 2, I would ultimately say that the limit altogether approaches infinity. So the limit equals infinity. Therefore, I would say the integral itself diverges, and we can't actually find the area underneath that curve. And that may be a little bit frustrating because if you're aware of what that picture looks like, 1 divided by square root of x is actually a graph that looks something like this. There's a vertical asymptote here and a horizontal asymptote here, and we're effectively trying to calculate the area underneath this curve towards infinity, and this graph looks an awful lot like some of the other graphs that we've considered, yet in this particular case we can't find the area underneath that curve because the limit itself diverges. It approaches infinity. So I'm going to wrap up this video now, and before I cut it off, I'll just point out something here that in condition number 2, we've effectively will complete the problem the same way. It's just that when you build your integral, you're imagining that the infinity value is here at the bottom of your integral, and you're bounded by some upper fixed value b. So that's why you'll see this suggestion of using a approaching, say, negative infinity is going to be used in its place. So just generate an integral with some lower boundary approaching negative infinity, and that'll allow you to capture your area as you move leftward down that image. For number 3, condition 3, we're imagining some arbitrary point C. It doesn't have to be at the peak of this curve. It can be anywhere that's well defined within the integral, and then perform 2 limit computations. One that computes the area going leftward towards negative infinity, one that computes the area rightward towards positive infinity, using infinity in your upper boundary, and then sum those 2 limits together. That would give you your area under the curve if the area can be computed. So again, if the limit exists, the integral is said to converge, and we can find the area. And if it's going to diverge, then the improper integral does not generate an area that we can compute. Not to say that there is no area, we just can't compute it. So I hope this conversation helps. If you have specific questions on your work, please let me know. Thanks for watching.